Okay, so today we'll be learning about electromagnetic induction, or induced EMF as it is also known. So let's review some of the things that we have learned about already. We learned that when a current is passing through a wire, it produces a magnetic field, and this has led to some of the most useful inventions in science. In particular, last week we learned about the simple DC motor. Electromagnetism can also be used for electromagnets. Electromagnets are used in junkyards. When cars are lifted up by those crane machines, they are attracted first by an electromagnet that pulls them up and then carries them over and drops them into the machine that crushes them and makes them into smaller, finer metals. And as we recall, an induced EMF is short for an induced electromagnetic force. You may recall that term from earlier in the school year, e.m.f, electromotive force. So first we look at an experiment that can be done that shows how a changing magnetic field will cause or induce an electromotive force in a circuit. So if you take a coil of wires and you push a magnet into the coil of wires, if you push the magnet such that the North Pole moves into the coil of wires, then the galvanometer that is connected to the circuit will register a slight deflection, meaning the pointer will move to one side. So the galvanometer, as you may recall, is a device that can measure tiny amounts of current, and it can also tell you which direction the current is flowing based on the pointer. So this indicates the presence of current flowing in the circuit, or what we call an e.m.f, right? It must have been induced when the magnet was moved into the coil. Remember, induced means that it causes something to happen without actual physical touch. So without the magnet actually touching the wires, it causes a current to flow through the wires. So the force of magnetism, as it is being pushed into the wires, then pushes on the electrons and causes them to flow. In other words, a current. Remember, that is basically what electricity is, the flow of electrons. Something to note is that when the magnet is stationary inside the coil, there will be no deflection in the galvanometer. In other words, no current is flowing. There is no induced current. When we take the North Pole and move it out of the coil in the opposite direction, the galvanometer will show a deflection the opposite way. What we can deduce is that the current is induced in the opposite direction. In conclusion, an electromotive force, and hence a current, is induced whenever there is a change in magnetic field inside a coil. This experiment shows that the direction of the induced EMF opposes the change producing it. So in other words, if the North Pole goes to the left into the coil, then the current will be acting to the right, such that it is the motion of the magnet that is opposed. And on the other hand, if you take the North Pole and move it out of the coil, in other words, you move the North Pole to the right, then the magnetic induced current will be to the left. This then brings us to Lenz's law, which states that the direction of the induced EMF is in a direction that opposes the change that gives rise to it. So key thing to remember is that it's in the opposite direction. That's Lenz's law. What are some things that can affect the size of the induced current? Well, first, the speed at which the magnet is moving. So if you move the magnet faster, then you're going to get a larger current. If you move the magnet slower, you're going to get a smaller induced current. If you use a stronger magnet, then you're going to have a greater induced EMF. A weaker magnet, a smaller induced EMF. If you use more turns of the coil, then you're going to have a greater induced EMF. It is also key to note that the greater the turns, the harder it is to actually push in the magnet into the coil, because there is a more resistive force since there is more coil, in accordance with Lenz's law. Remember that the induced EMF always acts to oppose the change which is bringing it about. So when you are trying to push the magnet into the coil, then the current that is produced opposes that action. So if there is more coil where there will be more current, then there will be a greater resistive force trying to stop the magnet from going into the coil. So we have Faraday's law, which states that whenever a conductor experiences a changing magnetic field, an EMF will be induced across its ends. The magnitude of the EMF depends on the rate of change of magnetic flux. And what are three things that we learned of that can affect the rate of change of magnetic flux? First was the speed of motion of the magnet. Second, the strength of the magnetic field. And third, the number of coils in the electromagnet. Lenz's law, the direction of the induced EMF or current, if present, is such that it opposes the change that gives rise to it, in keeping with the law of conservation of energy. So this leads us to Fleming's right-hand rule. So last week we learned about Fleming's left-hand rule. And Fleming's left-hand rule is used to determine the direction of the force on a current carrying wire in a magnetic field. So when you have a pair of permanent magnets and you put a wire in it that has current in it, the interaction of those two magnetic fields is going to produce a force that pushes the wire. So now this is the opposite. Instead of taking electricity and magnetism to produce a force, now we're doing sort of the opposite. We're taking a force and magnetism to produce electricity. So using Fleming's right-hand rule, as you see here, your thumb is the direction of the force or the motion. Then your index finger is the direction of the magnetic field. So you will line up those two first, and then, dependent on those two, your middle finger will give you the direction of the induced current. And that is all for today.